Okay, so I've already done a class for today. I totally forgot to hit the record button. So I'm going to go through this a lot more quickly than I did um, in today's class. So let me just go on ahead and give you a quick overview. I am going to quickly cover the thermal energy and molecular structure assignment. Then I am going to go through what my expectations are for today's quiz. I see 3 people have already completed that, so awesome. Kudos to you. And then I am going to discuss what we will be doing next week, and then for the rest of the remaining school year. We'll be moving into Classcraft. I know a lot of you enjoyed Classcraft or thought it was pretty cool, so we're going to go on ahead and go back to using that system. Also, too, the cool thing about Classcraft is that it has several features in it where I can set up like doorways and things that you have to have the right password or know the right answer to a question or a riddle in order for you to move on and things like that. So we will on Monday start a quest on Classcraft. So that's what this whole video is going to be about. I'm going to try and get this knocked out in about 10, maybe 15 minutes. So well, let's go ahead and start going. So the assignment that you started working on Monday was states of matter. Sorry, not states of matter, thermal energy and molecular structure. And about 6 of you have turned this in. I returned it to several of you who did about part of the assignment, maybe half the assignment, didn't complete it. Don't turn anything in until you complete it. I am not putting deadlines, hard deadlines on any of your work. Take your time with it. Don't work any more than 30 minutes a day. You don't have to anyways. And since you're not allowed to work more than 30 minutes a day, I understand if it takes you 4 or 5 days to complete an assignment. It's fine. I get it. We're all in a different spot right now. So don't turn anything in until it's completely done. And if you need help, show up to the morning AMA, ask me some questions on Google Classroom, or as you're going to find out here very quickly, or ask me some questions on Classcraft, and I will go on ahead and try and help you out. Complete whatever you need to complete, okay? So make sure you turn these in completed. All right, end of rant. The assignment that you guys worked on. So there was some videos, or a video and a PBS video that was on their website. I preferred the first one, but I put 2 options up there for you to kind of go back over some of the things we covered last week. And then your job was to draw the molecules, the molecular structure of a solid, liquid, and a gas. So what I expected out of that was something that looked kind of like this. So I'll just go straight to Google to give you a good example. Solid molecular movement, I believe, is what I did. All right, so solid molecular movement, I click on images, and boom, I go straight to this example because this example right here, I think really drives the concepts home, and maybe even this example a little bit better. So with a solid, what I want to see from a solid drawing is that maybe it's in a container, but that it is all stuck together and it is not changing its shape even though it's in a container. Because, and I'm going to give you the description for a solid now, solids have a fixed rigid structure. And the reason they have a fixed rigid structure is because each molecule, so my hand's a molecule here and this is a molecule here, each molecule is molecularly bonded to one another. So because of that, they stick. And if I have a bond in between, I can sit here and wiggle and do whatever, but we're staying together. And that's what makes a solid. Now, the moment those bonds break, and these molecules can now slide by one another, well, now you have a liquid. And that's what you see in this drawing here. Same stuff, same substance, but now the bonds have broken and they all fall down all on top of each other, right? And they just slide by one another. They might be loosely connected, like they're trying to bond, but they never can quite grab onto each other again and form that rigid structure. So that's what you would have for your description in that. And then for gases, once you get to the gaseous phase, the gas is moving about freely in the air, and it will fill the entire container. So liquids take the shape of the container, but with gases, because the molecules have so much energy, they're bouncing off every single edge of the container that they're in. Boom, 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 all over the place. And that's what characterizes a gas. They vibrate very quickly, but they also move very quickly in their environment. And if they're in a closed container, like a spray paint can, well, they're constantly bouncing off all the different sides, and they have so much energy that they're just boom, bouncing off of each other as well. So maybe in a liquid, like I said, they kind of are attracted to each other. That's why water droplets will form, right? Because they're all kind of attracted to each other, but they're still sliding by. With gases, they have so much energy that it's not even a thought to be able to grab onto each other and try and bond. They just hit and bounce. So that's what I was looking for your descriptions, and something similar to this as your drawing of the molecular structure. If you drew something like this, this would not have worked for liquid or solid, because I'm looking for what the molecules were doing. And this doesn't show what the molecules were doing. So, you could have had something also similar to this. These drawings are just as valid. I would argue, however, these don't make as much sense on surface level. So you kind of already have to know what a liquid is to understand what's going on in that drawing there. So again, that's why I like these drawings a little bit better, because now you have a container to put them in, and it shows how they behave in a container. So, all right, that's that example. So that was basically what I expected you to be able to do in 30 minutes on Monday. So that was number one. That's why it was a 3-day assignment. Then number two here, I was asking you guys to look up the boiling points and melting points for each of these substances. I'm just going to go over 2 examples so you can see how to do it if you didn't get this done. But all you do is you go to Senior Google and you say things like alcohol boiling point. And boom, it pops up. And Google actually has accurate results, and this point are on this little window here, so totally fine if you use those. And the same thing will do water. So you notice that's 173. If I type in water, voila, it's 212. So alcohol will evaporate sooner than water will if you're heating them both up at the same time. That is really important for what we'll be doing in mid-May for the final quest that I am building for you guys right now. I'm going to show you how we make liquid fire or alcohol. So, and how we not only make it using chemistry and biology, but then how we use our knowledge of boiling points and phase shifts to separate the two. So that's part of why you guys are going through this assignment right now, is so you can learn to do that later. All right, so anyways, that's how you guys find the answers to these. I believe the boiling point for copper is like 4,000 degrees. It's way up there. So it kind of shows you how drastically different substances are. That was the point of that assignment. And then the simulation, I figured you'd get 2 and 3 done. Kind of like this would be, you get halfway through this in a day with this together, and then the other half you would finish with number 4. So that's why I put this as a 3-day assignment. Again, I'm trying to stick to that 30-minute a day time piece I'm supposed to. So some of you were probably like, this is all I'm doing this week. Totally sorry for you guys. I'm being straight up. I'm doing what I'm being told. Okay. All right. So let's go into the simulation really quick. So there's some interesting concepts here that I wanted you guys to get from this, basically by playing around, because that's all I asked you really to do, is play around and then answer some questions. So when you go to phase changes, you'll see this finger here. I am able to reduce the amount of space in my container. That's important to know. Okay, so keep that in mind. Now, I'll bring it back to normal. The first thing I asked you to do is pump this up and add pressure. Well, if you start adding pressure, you if you pay attention to what is happening to the temperature, as you add pressure, the temperature increases. And I can continue to do this over and over and over and over again. So as I add pressure, I'm adding more and more molecules into this system. I am increasing the temperature as well. I'm adding energy into the system. And that's why that thing went from a solid suddenly to a gas, because I just heated it up. If I switch over to water, that's probably a better example there. And I'll go over to Celsius because that makes more sense for you. All right. So as I start to increase the pressure here, you can start to see I'm adding more water molecules in order to increase the pressure. And the more molecules are in there, the more they are bouncing against each other and the more energy and heat these things are acquiring, essentially. So I can keep doing this, and the more I add pressure, eventually there will be so many things bouncing off of the edges of this container so often that the container will explode, right? Another way I can do this is, instead of adding more water, well, I can increase the heat. So if I increase the heat, watch what happens to the pressure and watch what happens to the molecules inside. You notice they start spinning and moving around much, much faster, and the pressure continues to increase. So I can add pressure to increase the temperature, or I can increase the temperature to add pressure. And the reverse is true. If I cool this down, the pressure will go down. And if I add too much pressure, there will be so many things bouncing off the edges of the container, it will eventually explode violently, which is why, by the way, you don't put like spray paint cans and things near an open flame, because you increase the pressure until it eventually catastrophically fails, like it does in the photo here. Okay, so other things to think about. I can increase the pressure if I keep the amount of gas in here the same. If I reduce the amount of space, I get the same effect as if I were adding heat or adding pressure. So you can see as I push down on this, there's less and less space. That means these things are bouncing against the container more often. So again, that increases pressure. The more often these things are pushing up against the container, and because it's a shorter distance to travel, they're doing it more often, the more pressure you have. So this is an important thing for you to understand when we start making alcohol. In fact, this is a concept that a lot of the illegal moonshiners back in the day had to understand very well, or things would go kablooey on them and explode violently. And that happened quite often. So if you didn't have a chance to play with this and see how all of these things kind of interact with each other, play with it for 10 or 15 minutes this weekend. Get this in your head, because you're going to need to know some of this information, again, when we get into making distilled alcohol. Fuel-grade ethanol is what we are creating, stuff to power rockets with. We were going to, make the alcohol and then try the rocket project again. But unfortunately, we can't do that, so I'm still going to make the alcohol and show you and demonstrate to you that we could have used it for our rockets. So anyways, that was this part of the assignment. Finally, the equations for photosynthesis, cellular respiration, and fermentation. We know that the equation for photosynthesis is 6 CO2 plus 6 molecules of water, H2O, plus sunlight. And that's not how you spell sunlight. Okay. And that turns into glucose, oxygen, and that's it. That's the equation. Fun stuff, right? And we talked about this a lot in second quarter, and we even talked about it in third quarter. I brought it up a bunch because it's the most important chemical equation on the planet. Without it, nothing that you know of exists right now. Not the wood that makes up your table or your house. None of the food None of the animals that are on planet Earth right now and none of the plants would exist without this equation. So it's the most important equation in the known universe, as far as we're concerned, as life forms here on Earth. So, okay, so then, well, what is cellular respiration? Well, that's glucose plus oxygen, and that gets turned into CO2. Same numbers, by the way, 6 CO2 plus 6 H2O. Only this time, instead of sunlight, you get ATP, which is the energy that the cells use. And this is important because without this equation, you wouldn't be able to get energy from your food and you wouldn't live. You would die. So cellular respiration is really important for all life that consumes other things, which is most of everything other than plants. So it's a really important equation as well. Now, the equation that we are going to be using has to deal with yeast. And yeast, for them, they can't do cellular respiration. They're too simple of organisms. They're tiny little microscopic organisms. You can't see them with your naked eye, okay? They're very, very tiny, and they're very simple. And the glucose molecule is too big for them to munch on and break down like we do. So what they have is a different equation, and it's called fermentation. And this is the equation right here on my screen. So this is the glucose molecule. There's those 6 carbons from the 6 CO2s, and there's those 6 water molecules that got stuck together to make your glucose. Well, when yeast eat it, they're only able to pull off 1 carbon. And that's where they get their energy, by taking off a carbon and creating CO2. And they have to have 2 glucose molecules in order to create 1 CO2 molecule. So they're not very efficient at breaking down sugar at all. The great thing is this little molecule that I'm circling with my mouse, this is ethanol or alcohol. And this is how we get fuel grade, like stuff you would put in a car to burn or a rocket to burn, ethanol. Because we all know that ethanol is flammable, alcohol is flammable. So this is basically how we get all of our alcohol. In fact, this summer, it was in November, I went to an ethanol plant where they take corn and they use corn sugar, essentially, from the corn, and they make ethanol out of it. And then they have a molecular sieve that has these tiny little clay beads that go and grab the last 5% of water out of it so they can make 100% ethanol. And I'm in a quest that I'm creating for you. I'm going to have some of the photos and videos of the stuff that I saw there too. So it's kind of cool. But anyways, this equation is why we are able to essentially harness biology to make, or harness biology and chemistry to make ethanol. So there you go. That right there kind of covers your assignment, your thermal, energy, and molecular structure assignment. So you guys now have all the answers for that. You should be able to get it knocked out if you haven't yet. Let's go on ahead and move on. Next is today's quiz. So today's quiz, this is not going to be graded. I'm going to give you feedback using Classcraft here probably next week on the answers that you put in here. But this is not graded. This is so I can see what you've learned. So on this one, don't use your notes if you can keep from using them, because I want to know what you know. So, and that's all this is just to make sure that we're all on the same page, so I don't cover things that I don't need to cover, or I don't move on before you guys are ready. So this really quick, a breakdown of it. You have to explain how you know what state of matter this is up here for each of the states of matter. So give me 2 pieces of evidence, like how you know blank is a solid. Okay, how do you know? Tell me. In your own words, describe what temperature measures. So we've been kind of talking about this, and that's what those simulations were for and things like that. So I want it in your own words. And then with this one, I want you to, I'm clarifying this question. I want you to explain why what the molecules are doing that finally allows them to go from solid to liquid. What is it that all of a sudden makes those molecules no longer want to hold on to each other and go into a liquid or suddenly go into a gas? So we're talking about the molecular structure of these things, what these things are doing, their motions. Okay, so that's the quiz for today. Once you get this quiz done, you're done for the weekend because tomorrow there's no school and then it's the weekend. So then I'll see you Monday. And on Monday, what we will be doing is getting into Classcraft. And to remind you guys what Classcraft is, it's the thing that we used at the very beginning of the year. On here, there are quests for you to do, and you have your own avatar and everything else. To get logged in, remember, you need to use your @m.kckps login information. That's how you get in here. So the same way you get into Google Classroom, same login to get here. We are Tamriel Genesis 5. That's my 5th hour class. And when you get logged in to this, I'm waiting for it to load up here. The place you want to go is quests. So quests, when you click on quests, this is where your assignments will be from here on out. And I want to mention these quests here that you see on the screen now, they won't be here on Monday. So these are going to be gone. And you are going to see one brand new quest right here on the central island. And this is going to get you ready for what we're doing in May. So these quests right here won't be here. You'll have a new one. Just to show you what these, or to remind you what these look like, when you click on them, there's a path with different things for you to do at each step. I'm going to try and make these so each step should take you about a day, maybe a day and a half. Okay, so 30 to 45 minutes is about the amount of time it's going to take you to progress each step on here. All right. The other thing to mention is the messaging system. If you have questions from here on out, don't ask questions on Google Classroom. Go to Classcraft and click this messaging button. And the reason is, if I have somebody with a question, if you type it in, I will be able to see both here, it shows me, oh, I have a message, and then I can see who has the message. And this is a heck of a lot easier to see that, oh, somebody's trying to get a hold of me than Google Classroom. Because on the Google Classroom side, I don't know if you notice, but when I go to my stream, there's no way really for me to know that somebody's commented on here recently unless I go to each post, click the class comments, and see if those are recent. I don't have like a little notification bar up here like I do with the app, like the iPad app and the phone app. It actually has some a notification system on it, but the desktop doesn't. And for me, it's just a heck of a lot easier to go jump on Classcraft real quick. So like, you know, if I'm doing my morning AMA and nobody's logging on, but I want to have some content up for you, well, I can jump on here and go, oh, look, I got some messages. Well, I can answer some questions on my AMA and do it that way. Okay. So, and it's real nice and quick, and I can check all of my classes in less than a minute, as opposed to going through each individual post for each of my classes to see if somebody commented on them. So, anywho, make sure you can get logged into Classcraft. If you can't, get a hold of me however you need to get a hold of me, either via my email, which is christopher.clemens@kckps, or you can send me a message for now on Classroom, and I'll help you get logged into Classcraft. So that's all I've got for you today, and I will see you all next week. Have a wonderful weekend.